And a very good evening, everybody. This is Paul, NO0T for the Front Range 6 Meter Group. And tonight we are fortunate enough to have Scott McIntosh from the NCAR, I can't even say it very well, National Center for Atmospheric Research. You can say that better. And Scott's going to give us an update on what's going on with the sun these days. There's a lot of activity going on, so take it away, Scott, and give us your best shot.
All right, I'll do my best, Paul, and thank you again for, can everyone see that okay?
Yep. Yes, sir.
All right, so I've changed my, oh, go away. I don't want to know that this meeting is being recorded by AI. Oh, it's sitting right where I don't want it to be. All right. All right, I've changed my backdrop, because we're on final approach to solar maximum. So I hope that that plane is actually landing and not taking off. That's all I can say. There's a little bit of a 180-degree ambiguity. So anyway. All right. So really, thanks very much, Paul, for asking me again. I think we're on our 842nd update at this point. So I'm just going to say briefly, a lot of the faces are familiar. My apologies if this is the first time you're hearing any of this nonsense. Because I'm going to skip over my usual half hour introduction so that we can get to some fun stuff and show some of the implications of what we've been looking at and start to explore things at a little bit of a deeper level. So anyway, I've been having a lot of fun with this in the last couple of weeks. On Friday night, I was in Cleveland with the Ham community. I don't know if any of you are aware of that group run out of Case Western in Scranton. That was pretty fun. I gave the keynote talking about forecasting cycle 25 and where things were. And so some of this is cobbled from that, and some of it was scrambled together at 3 p.m. this afternoon after I did my regular monthly update. So hopefully this makes some sense. So here's the thing that we're all trying to understand, right? So this is the butterfly diagram on the top and the sunspot number on the bottom. This is actually a bit out of date, a bit more than almost 15 years out of date at this point. So the idea, of course, is we're trying to understand both of these things at the same time, the progression of sunspots with latitude and then how they contribute towards the amplitude of activity and various other things. So we became infamous in 2020. And I think I've been talking to you guys, Paul, since about 2021, I think, maybe. So just this is kind of where we met, where things were. And we had produced a kind of I don't know, revolutionary, certainly not evolutionary forecast of what the present sunspot cycle was going to look like. And it was dependent on a particular event happening. And this group has had the great joy of riding along with us since then. I think we probably even talked just a few days after that event had happened. And that allowed us to, of course, alter our forecast for cycle 25, and we got to here. So, well, at the start of the game, we were looking at, we're all really excited. We're going back to the heyday of ham radio in 1957. Cycle 25 is going to be one of the 5 highest of all time. And just like everything else to do with the sun, just when you think you got it all licked, it kicks you in the square in the hoo-has, right? So we waited for a particular event to happen. That event we called the Terminator. This is basically the end of the sun's 22-year hail cycle. We are still the only people that are looking at this thing, believe it or not. It happened in December of 2021. Hopefully I'll show that in some of my graphics a little bit later. And that meant that we had to adapt our forecast. It was about a year later than we had hoped. But that still put us round about the mean sunspot cycle. So this is where things stand then relative to that. So if I go back, boom, 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 this is where things were before 2021. This was things as of yesterday. Okay, so you can clearly see that the blue curve is out. Okay. I think we're actually already had the first peak of maximum. I think it's hard to tell. You can only really tell that after the fact, but I think we've already had the first surge of maximum. We're hopefully, cross your limbs, we're on the second phase of that right now, and we'll get to that a little bit later on too. So, if those of you that have been with us since the start will remember, up until the middle of last year, this thing was really tracking great. And then the sun decided, I'm going to take a wee break. This is a bit strenuous for me, and slowed itself down a little bit. And it's now starting to claw its way back up again. But it's kind of interesting because, as I'll show you, a lot of the activity measures are significantly higher than cycle 24. So even though this one isn't breaking the record books, it's definitely massively outperforming its predecessor at a level that wasn't anticipated. So you've seen this and that, and I think maybe I updated this since the last time we spoke. So this now includes sunspot cycle 25. And so this is just a little animation of the sun's 22-year magnetic hail cycle. The top plots are the sunspot number, so total number in black. Red and blue signify the hemispheric sunspot numbers. And so it's purely an illustration of how these large-scale magnetic bands are observed and what their motions are. And then, of course, we kind of infer that those red and blue things are the underlying magnetic polarities, right? So you can see that basically there's what at face value looks like an interference pattern going on, and the interference pattern ends up being the sunspot number. So these big magnetic systems interfere and play with one another, and the resulting sunspot number is the interference pattern. Of course, there's a lot more intricacy going on. The big, I guess, Paul, the big ideological battle is that in a conventional model of what's going on in the sun's interior, this probably shouldn't work. Okay. So what we're kind of testing out in real time is a hypothesis about how the sun's inside works. This work would lead you to believe, and I'm not getting into a lot of the detail right now, is that these large-scale magnetic systems interact strongly with one another. The conventional models would have you believe that they're completely passive, right? They don't interact at all, right? And so there's a kind of that sounds a wee bit nuanced, but that's the dichotomy. That's where we're at. Okay, so these are really two camps. One of the things that we've been playing with is this idea of statistical superposed epoch analysis. So this is all new stuff, Paul. So strap yourself in, right? So all we're looking at here is we're trying to understand the average behavior, right? And one of the big challenges with the sun, and some of you have heard this before, it's very easy, relatively easy to develop climatologies for like Denver's weather or Boulder's weather or wherever you happen to be's weather, because the orbit of the Earth around the sun is always fixed. So the clock is always fixed. For the sun, that's not so true. What we've discovered is that this underlying hail cycle is very robust, but the interference pattern that it produces is not. And so the clock is actually variable. But what we've identified is that so this examples, you see those green boxes running across the screen? Those are plus or minus 11 years based on those red dashed lines. The red dashed lines are these terminator events. And you can see that as I scan across, you can see that those butterflies of sunspots as a function of latitude actually are pretty well behaved. They're not as random as you might believe. So if I take these, 14 samples and statistically add them, I get something that looks like this. This is the average sunspot butterfly diagram. Okay? Now, if there's any kind of predictive capability to this, which is kind of what we're after, right? We're after trying to play the star forward. If I add the data, the most recent data, it should sit right on those curves too. How did it do? It does pretty well, right? So as long as you understand what the clock's doing and how the clock moves, there's actually some predictability to this thing. So at least in terms of latitude, longitude, longitude's a different story, but in terms of latitude and time, the sunspots of cycle 25 are behaving as one might have hoped. Now, if I take the statistical average of the sunspot number, it looks like this. So these are all normalized. So I normalize everything between 0 and 1, right? And then I also am crafty. I normalize time as well. Okay. So remember, this thing is plus or minus 11 years. I've got an animation of it coming up just to help you. So exactly the same process, but on the sunspot number. The average sunspot cycle is now scaled to our relationship that we found in 2019. So that puts our peak sunspot number somewhere about 160 with a variance of about 30 each way. And the red triangles there are the actual observed data. So I'm not sure if I think I might have shown this one before, but we've been this was kind of also frozen in early 2022. So there's nothing changing on you. There's no sleight of hand. The sun seems to be following at least what the statistics would identify. So we're probably on a pretty good track. So this is the F10.7. So the solar radial flux. Okay, so the thing that we use as a proxy to understand what the thermosphere is going to do and the ionosphere is going to do, so that we can understand better propagation characteristics. So again, you see the impact of these vertical dashed lines on F10.7. At each one of those vertical dashed lines, the solar radial flux goes through 90 SFU identically, right? So there is a step function in the data. The sun totals along the bottom, and it goes up to a new plateau and then starts to rise. That happens identically at these terminator events. That will someday we'll get into the opposite side of that when it goes back through 90 SFU on the other side. That's kind of fascinating as well. Just to make you all absolutely sick, here is the representation. I've been playing these games with statistical studies, so I'm going to re-baseline time. But the fun bit is I can express time as the position on a circle. I know that sounds a wee bit wild, but this is what it looks like when you take that 1947 to present data using a Hilbert transform and express it on a circle. So important lines on this plot. So you can see that the circle is divided up into 5 parts. The first part sits off it's sitting at about 1 p.m. You can see the radius going out. I can't make the cursor work. And then you've got another one, 1/5 of a circle to the left of that. And then a green one, a fifth further. And then another one. And you look at and of course 0 is horizontal. Okay. 1/5, 2/5, 3/5, 4/5. 4/5 is identically solar minimum. Okay, statistically. So you can see how this thing just springs into life after the terminator event, which is 0, gets really strong, and then starts coming down again and drop into solar minimum like values around the green line. So just to remind you, 0 flat is the white vertical dashed lines, and the dotted lines you see are that green dotted line, right? So it basically switches off. This
So
is
Scott,
when, yeah,
is
go ahead.
is this 11 years all the way around?
Not quite. Sometimes.
Okay. So it's Terminator to Terminator in one loop.
Yeah. So the terminator to terminator can be broken into, the time can be scaled onto position in a circle.
Okay, and then you're talking about the arm at about 7:30, 8 o'clock as being
That's the off position.
that's the off position. Okay, that's how I
Right.
saw
So
it.
that's all right, Mike. How you doing?
I'm great. You
Yeah, could be better, but
living the dream.
yeah, always, dude. So basically, there's someone in the inside of the sun throws the big switch, and that's the point where activity switches off. It's kind of cool, actually. You see it in all the different measures. Just to illustrate, now it's really crap because this is annual data, but it's annual data going back to 1757. Oh, there's my buddy. Hey, Peter.
Oh, hi, Scott.
Have you got a question, or are you waiting for
Yeah,
the
I do
last
have a question,
day's
but
worth?
you might want to
Okay.
finish your thought there.
Oh, I was just going to say that this is now the same thing for the sunspot number itself, right? So
Yeah.
it's the same diagram. Horizontal's the terminator, solar maximum at 1 p.m. at 1 o'clock, and then off at about 10 o'clock is there, and then the green line again is the switch off. So the switch off is not a fluke. Yes, go ahead, Peter.
Yeah, so my question relates to actually the 10.7 centimeter. I know this Art Covington started this sometime, well, 1947.
Yep.
Is there any other source around the world that has been monitoring the sun like this at a different rate, different frequencies?
I don't think systematically, Peter. So I think that the Koreans also have a 10.7 centimeter dish. And they're systematically observing because they want to understand, drive their own models with it. But other than that, it's actually a conversation that we had in a meeting that I can't talk about yesterday.
Okay.
So we actually talked about building redundancy into this because at some point, DRAO struggles for funding from time to time.
Yes, indeed.
Right. And so the idea is that where else could we stand up a capability that could be cross-calibrated with DRAO and it would be funded in perpetuity, right?
Is Ken Tapping still operating that?
Yeah.
Yeah. Good.
Yeah.
Thank you.
No,
Thanks.
that's a remarkable guy right there. So
Yes. He loves opera, you know.
does he?
He's
I'll wind him up
great
about that.
fan of opera.
Okay. I'll give him grief next time I see him. It's been a while. So anyway, so some of you have seen this plot in the past. So much like we did a statistical average for the sunspot number, this is the statistical average for F10.7. Right? So this was the feature of our Radcom article back in 2020, July of 2022. So that's what the data looked like at the time. And those of you who have been along for the ride will know that it's been creeping up, and this is the data as of today. Right? So actually, in the forecasting language, this is a 75% skill over 4 years. Right? So we're 75% accurate, which is pretty damn good, actually. The blue curves are the monthly data and the red curves are the daily data. So it's not getting every bump and wiggle, but given that we haven't adjusted the forecast at all yet, it's not too bad. In fact, it's better than anything else that's out there. So something to be relatively proud of. So anyway, the other thing that's interesting here is, I don't know, there was a conversation a while back talking about the double bump. I don't know if anybody remembers that, but we think we understand now where the double bump's coming from. And so we're fully anticipating this thing to turn back up again. But there might not be an accompanying bump on the sun. Right? So sunspots and things. It's something a little bit more sneaky than that. It's not terrestrial. It's not terrestrial.
Is it from a constructive destructive interference?
No, we think it's cycle 26. So cycle 26 starts to appear in plage at high latitudes. Right? So when we get through maximum, cycle 26 starts to appear, we should be able to, within a year, we should be able to see it, right? So this whole big, long progression of the Gale cycle, Mike. And we think that that's what you're seeing in this statistical bump on the downside. So F10.7 has 3 different contributions. I think there's like a background cyclotron background, like, and then there's the coronal emission, synchrotron emission, and there's photosphere, corona, and some of chromosphere in there. And so you're looking at 3 different contributions. And so on the downside of a cycle, you get a contribution from the upcoming cycle, just to really F with everyone, right? And this is probably why the sunspot number itself is not a pure proxy for F10.7. Right. So there's been a lot of discussion in recent years of people freaking out that F10.7 isn't following the sunspot number anymore. Right. There's probably a reason for that. And it's called physics. But anyway.
So does that point to a quicker terminator, which would in turn point to a stronger 26 then, Scott?
Oh, you're following along, Chris.
Well, just thinking out loud.
No, it's a great question. I'll be able to tell you in a year. Right. So the 2 hemispheres are still well synchronized. We should see cycle 26, I would say, before the end of the year, maybe. With great, it's all about fidelity, right? And then once we see it, we'll know roughly know statistically how long they take to get to the equator. I'm going to get into that a little bit from my buddy Peter, who's interested in ice cores.
Yes,
Right?
indeed.
We're going to blow shit up, Peter, at the end of this, all right?
Yeah, I'd love to do that.
We're going to go
Mike,
viral. Paul, we're
I
going to go viral. How's your server?
Sorry?
How's the server? We're going to go viral.
Oh, well, we can manage.
All right, okay. So anyway, so here's
I just wondering, sorry, Scott.
yeah, go ahead.
Are you seeing some evidence of 26 in the Hale cycle changing?
Not yet.
Oh, you're perceiving something.
Yeah, I mean, I think right now we're aiming for a terminator in the 21 to 22 range. 31 to 32 range. Right? Because that would, if it was just average, Peter, that's about when it would happen. Right? But I'll get into this a wee bit later on because it's all to do with the ice core sample work.
Okay,
right?
well, let's talk more about that later.
We'll get to that later on. So Chris wins the award for most perceptive question so far, right? So here's the geomagnetic indices, and you'll see that these buggers go quite a ways back. In fact, it's interesting. So if anybody ever wants to join me in the British archives, I'm actually going to go hunting for the letter that why the hell did the magnetometer network set up after the Carrington flare? That's my question to you all, internet sleuths that you are. Could it be anything to do with the East India Company? I don't know, maybe. Remember what happened with Carrington? All the telegraphs went out, right?
Yep. So
anyway, so here's the monthly top plot. Here's the monthly AA index. So it's a geomagnetic index. You can see that this thing is roughly, well, it's very correlated with the sunspot number, but it has an underlying trend. The bottom's AP and KP. So instead of being average between, so I think AA is noisy because it's an average between 2 points. AP is 9 points and KP is 9 points too, but it's just a different measure of magnetometer readouts. If I make my crazy polar plot, it doesn't look much there, right? You can see that it flattens on the downside of the cycle and it's high. You know, you would think that it's a bit of a statistical mess. It's not uniform. There it is at the monthly cadence. You can start to see that it has several peaks and troughs, actually. Do you see, if you notice between 11 o'clock and 8 o'clock, it's enhanced. You see that? What do we know that happens on the downside of cycles? Coronal holes, right? This is a big signature of the way that the sun changes from dark side to light side to dark side activity. So it goes from the solar wind starts to take off. So that's what's driving the geomagnetic indices here. And apologies that this is playing backwards. I didn't do it deliberately, I promise. But this is the idea that now can we build a statistical model for the AP index and compare it to what we're seeing. There's the statistical average of KP. So again, I'll walk through the first. So this is the cycle divided into fifths again, right? So 0.2 is solar maximum. 0.4 is not. 0.6 is the turnoff. But this thing statistically peaks at 0.4, right? So sometime between solar max and the switch off, you're seeing the most intensive geomagnetic storms. It's probably to do with the whacking of the magnetosphere by the solar wind, right? To do with these big coronal holes. Anyway. Just to show that this kind of statistical nonsense works, this is what cycle 24 looked like. So it fits rather well within that wild envelope. Okay. We're not making any big song and dance about this stuff. This is just, it's interesting. There's cycle 25. Okay, so it's generally more active than cycle 24 was, and we're not even at max yet. So remember, max is about 0.2. So we've still got a ways to go to the max geomagnetic. People ask me a lot of questions about flares, and cycle 25 is massively outperforming its predecessor in terms of flares, right? So look, if you look, and I think I screwed up some of this stuff. Look at the number. So in the top left-hand corner is the C-class flare number. There's more than double. And in M-class flares, there's more than double. In fact, there was some ridiculous, like 16 of them yesterday. There was a lot. And then, of course, we had that little burst. And I think I generated these plots when we had the little tantrum a few weeks ago. And so the X-class flare number is not quite double. But at this time, this is basically the first 2 years of comparing the first 2 years of the cycles. And it's, cycle 25 is outperforming its predecessor. Not going to read this slide, but some of you will be familiar. This is us talking about, okay, where is solar maximum? When? So it's not where or what amplitude anymore. It's now when. And so we've been tracking a lot of coronal morphology in the sun's polar magnetic fields because those are indicators of coming into land, right? Final approach. And you can see in that panel B there that the polar magnetic fields are tottering around 0, which means that the polar reversal of the magnetic fields is happening. The polar coronal holes are pretty much gone, which is another indicator. The thing called the polar crown filament is sitting about 87 degrees latitude, and then all of a sudden it'll just disappear, right? So if you ever get a chance to look at any H-alpha imagery of the sun, watch out for a little tiny tuft of stuff way up at the pole. And with the sun tilted over, I think it's north prevalent to us right now. I can't remember exactly. You can see there's a tiny little tuft of stuff right at the pole. And that's the polar crown filament. But that starts its march from 55 degrees latitude. And it started at the terminator. So you can see that in this plot at the bottom. That's basically tracking out the evolution at the pole. As of last Thursday, here's the solar polar magnetic fields. You can see that this is from Wilcox Solar Observatory down in Palo Alto. You can see that the polar magnetic fields are pretty much 0. If I look at the same plot coming now from a spacecraft, so it doesn't have the same seeing and it has much higher resolution, you can see that even the spacecraft is saying that the polar magnetic fields may be about to proceed away from 0. So when they proceed away from 0, that means we're done, right? So, but if you look at cycle 24's transition right about 2014, you can see that it hangs around zero for, over a year, right? But if you remember, cycle 24 was massively asymmetric. Right? The north peaked way early and the south came in way late. So that reflects, that is not a typical transition for the polar magnetic fields. Right? So it's just interesting, kind of getting into some new diagnostics. This is a new kind of predictive diagnostic that we're looking at. Is like, okay, so here's the last 3 cycles. And as Chris would point out, these are terminator to terminator, right? So what we are looking at basically are the Hale cycle progressions here. You can see where the data was today. If I compare it to sorry, I'm making everyone sick. The crazy underlying Hale cycle looks pretty good. It's not bad. I mean, it's not meant to be perfect. It's just an illustration. Go ahead, Peter.
I'm just wondering if they the cycles sorry, the cycles you're seeing are related to any changes in the solar magnetic field that like relate to things like the Spohr minimum or the Maunder minimum. Can you explain any of that with the analysis of the way you're looking at the solar cycle now?
I'll get there later.
Oh, okay.
All right. Have you seen these slides?
What was that?
I said, have you seen these slides already?
No, I haven't.
I wondered if you had some little bug on my machine here.
Okay, I'm just being a little prescient then.
No, it's good. Yeah, no, totally. You're totally on it. So you and Chris are in a competition right now. So
No.
So here's the underlying sunspots, right? So it does look at the kind of beautiful framing of this stuff, right? Those vertical dashed lines are the turnoff points, right? And where we think it really impacts F10.7 is that there's still spots that come after that point in time, but they're no longer complex. And if you're talking about emission, coronal emission, it's complexity that matters. It's how tangled the magnetic field is, how stressed it is, gives rise to those radio frequencies, right? So anyway, we're just playing with this right now, right? Because the idea is, of course, it won't get interesting till about 2028, but we're going to keep tracking it anyway, right? It's because we're watching for that, because our next thing is, can we predict the turnoff? Okay. So there's everything kind of superimposed. I'm actually pretty happy with that. If I'd drawn that back in 2012 when we came up with this, I'd be stoked. Here's a bunch of butterfly diagrams. I'm not going to explain everything that we're seeing here, but this just shows a whole range of different wavelengths and a range of different measures. The complexity of multi-scale magnetism that's going on. But it's all triggered by the Hale cycle. You'll see I even threw coronal holes in there, right? That's a new twist to the picture, right? That's what the last paper is going to be on. Is the dark side of solar activity. We're working on that one right now about the AA index and F10 point, all these kind of stuff. This is why I've been generating a lot of new plots. So anyway, it's just an illustration. So I don't need to go over this again, but you guys have been browbeaten for too many years now. This stuff is all, at least to us, I guess, I hope it's getting a little bit obvious. The impact of the Hale cycle, the visibility of the Hale cycle, probably the interference of the Hale cycle too is sitting there. 55 degrees is still important, yet nobody gives a toss. Interestingly enough. We know about the rapid jump in all the proxies. We think that this kind of validates our model that the Hale cycles interfere with one another to produce the sunspot cycle. That is a huge problem. And of course, again, the terminator separation is a measure of the interplay of the cycle bands, and that's the thing that kind of ultimately kind of controls the amplitude. So we're going into some uncharted territory now. Okay. So here's where things are. Here's our crazy infographic, right? So this is illustrating that this song remains the same, right? There's nothing abnormal happening at all. This is just how large scale interfering systems work. That's it. That's what's going on. So as best as we can track it, it provides us with capability to forecast it. Are you ready? Here's the future. There's cycle 26. There's it becoming visible in the 24 to 25 timeframe, right? As best as we can do. And of course, we're waiting on Arnold again, right? We've got a long wait. Probably in that 2031 range. So there's the data that I showed earlier, first slides, against everything else. So again, things are tracking. What I really want to do next is to be able to draw that vertical dashed line where things switch off again. Right? Because I think as much as the Terminator is beautiful, it's a sledgehammer. What's happening on the downside that makes things go to sleep? And I haven't shown you the flare statistics. When you plot the flare butterfly diagram, it's very, very clear that something switches off. And it's to do with where those bands happen to be in proximity to one another, which means that they probably interfere. They really do connect. And that invalidates whole classes of stuff, right? That's a discriminator of long-standing models. Now we're getting into Peter Land, right? So it's maybe Neverland, Peter. I thought you probably thought it was Neverland, right? Okay, so where's this all going? And some of it, one of the things, remember this idea that the Terminator separation. So the Terminators here are the vertical dashed lines in the top plot, right? Also in the bottom plot, but the bottom plot's messy. But the top plot, you can see the kind of compression and rarefaction of the Terminators, right? You see that round about 1800 they get separated, and we go into what they call the Dalton minimum, and then as we get into the modern maximum, they become a little bit compressed, right? So it's like a barcode almost. Anyway, and so you can start to see, if you look at the Hale cycles down at the bottom, you can see right about 1800, 1780s into 1800, and through the Dalton minimum, you get this weird where one cycle has really eaten into the others. So if you see that cycle 4, so you count from the left, not counting the first one. So 1, 2, 3, 4, and then you get this big separation. And then 5's not separated as much, but the amplitude's already down. Funnily enough, we see the same kind of thing from 23 going into 24, right? Now you ask yourself, why the flip is that, right? Because this is one of the big questions, like where did grand minima come from? And if this hypothesis is going to hold water, it kind of has to explain where grand minima come from, right? Who remembers our favorite Hilbert transforms? Okay, so this is how we detected the Terminators in the first place, right? So the Terminators are basically where the phase function just completely flips sign. We can move it around so it's a zero crossing or whatever, but in this point in time, it's a flip of sign. It goes from minus pi to plus pi, right? Or -1 to 1, right? Look around 1790 in this plot. Look at that elbow in that phase function.
Mm-hmm.
Right? Look at all of those cycles. And then look through all of history. Right. Well, yeah, pretty much. This is pretty much all of observed solar history. And look at cycle 24. There's a knee in that guy too. Right?
Mm-hmm.
All right, Peter. It's your moment to shine. Right? Those yellow dots are McCracken's major geomagnetic events identified in ice core samples.
Yeah.
Right? And those ones in 1794 are the biggest of all time. And there's 4 of them right on top of one another.
Mm-hmm.
Right? These things produced, I've found the papers that talk about aurorae, rampant aurorae over Mexico,
Yes.
right? 15 degrees latitude.
So we're due.
Who knows, Mike? I don't know if I'd go to Vegas on that one. But, and here's the one for interesting meteorologists in the room. What else happened in 1794 into 5? It's the biggest El Nino ever. Ever. And then a decade later was the year with no summer.
Yes.
Right? But that one's more volcanic. Was that Krakatoa? I can't remember.
Krakatoa. Yeah, Krakatoa.
Right. So that was the year with no summer, but you'll also know there's some huge geomagnetic events there too. So yeah, you get a doubling down of things. But it's kind of interesting, and I'm not sure this is when we finally have our conversation about this. I'm not sure how reliable the contemporary records are compared to McCracken's analysis, because there's way too many of them, and I don't know. I'm not enough of an expert to compare apples and apples. So those are the kind of teal colored dots, right? Because McCracken's analysis was published in 2001. Is that right? I can't remember, something of that order. And the blue dots are a contemporary analysis, and I'm much more confident in the old ones because they could see the Carrington flare.
Yes.
You can see Carrington sitting right there, 1859. The interesting thing about Carrington was it was in the ascending phase, but it was near the equator. It wasn't very high latitude.
These are events so that struck the Earth, right?
These are massive geomagnetic events, Mike.
But did they also strike the Earth? So they're just geomagnetic?
Oh yeah, they left something in the ice cores. Yeah.
Okay. But there could be others, but they didn't hit the Earth, so
Well,
we're not aware of them.
Right. And you exactly. So there's a very strong sampling effect, right?
Yeah, it's
There's
we're
very
pretty
strong.
small. We're
one little dot in 3-dimensional space, right? So, and that of course really skews the statistics, right? But that's also why people will tell you, oh, there was a Carrington flare that happened in 2012,
yeah.
right? But fortunately, the Earth wasn't in the firing line. I'm not sure I buy that, but anyway, it makes for great press. So, so this is a real problem, but we're kind of getting into nuts and bolts here. One of the things that something has slowed down the system, right? So you get these, there's a huge cycle right before number 4. 3's massive, 4's big, 5's a wiener. In fact, a lot of people, all my colleagues talk about there is actually no 5, right? There is a 5, but they talk about cycle 4 is so long. Was there a 4A and a 4B? Right, which is kind of preposterous, but something has gone off that makes the amplitude of the next 3 cycles small. And then it kind of goes back to average, right? This is your Nobel Prize right here.
Mm.
Right?
Aliens
So just to illustrate.
Aliens ciphered out all the fuel for something.
Dude, it's all about fuel. I'm not sure about the aliens though. But that we can make this viral. What's up, Peter? You're gesticulating like mad.
Yeah, I'm just wondering, over time, is this changing at depth in the sun? And do we know how deep into the sun?
I don't know. We'd have to actually model this thing to figure out why, right? What I think's going. Yeah, let me go through this and then I'll get to where I think we're going, right? So here's now. So the middle 2 panels here are the same thing that was on the previous slide. And all I've done at the top and the bottom is zoomed in on areas of the Hale cycle. And the idea is just to illustrate how this compression and rarefaction of the cycles is going on. Remember that my underlying hypothesis is that the bands interact with one another, right? Right? They know about one another. In the contemporary models, they don't, right? They're just there. They're passive. Now, and remember there's a longitude problem here, right? Well, lights are flickering. That's no bueno, right? So there's a longitude problem. Man, what is going on? Right. So there's a longitude problem. And so I'm not factoring any of the longitude issues in here, but there's 3 or 4 huge storms happen on the downside of cycle 4, right? What we know about magnetic fields when they interact. So if I destroy half the magnetic field, the progression of those things towards the equator is going to slow down because it's their mutual interaction that may be pulling them. Right? So this is controversial, right? That the bands experience an electromotive force that would pull them towards one another. They're not being moved by circulation. So if I destroy enough field, I'm going to slow that bad boy down. If I slow it down, I'm going to push it to the right. I'm not going to pull it to the left. I'm pushing it to the right because the thing's going, right? Which means it's going to eat into the growth time of the next cycle. And what's that going to do? It's going to quench it. The problem with these guys is it keeps happening. And so the next ones are quenched. And then we have a like a quiet spell. You see that? There's 2 cycles where there's almost nothing. And then boop, it pops back up. Right? So one of my pet projects for next year, if I have a chance to do it, I want to go to the Admiralty in London. And I'm going to start trawling through ancient sea records for reports of aurorae, right, at very low latitudes. And I'm going looking in the 1600s. Now, I've got a very narrow search in mind. What could I be going after? Any thoughts? It begins with Maunder. Ends in minimum. Was the Maunder minimum triggered by extremely massive storms? You know, we know there's not many spots, but what got the sun into such a frankel? Right? There's all kinds of hypotheses out there. This one's equally mental, right, to all the others. Anyway, so back to Peter's other question. So he's been waiting a long time for the ice core thing, right? So there's another cycle on the sun called the Gleisberg cycle, right? It's hypothesized, right, that the sun has about an 80-year wobble. And there's many ways of observing that wobble, whether it's the hemispheric. I actually like to think it's sloshing. So the idea is that the hemispheres are very nearly balanced to one another, but it's just slowly teetering. Slowly. And that slow teeter produces a very low amplitude oscillation, right? And here, this is a not unique, right? But this is a plot of the sunspot number from 1757 to the present. And all I've done is figured out what the average maximum is, and it's 171. And all I'm doing in the bottom plot here is plotting the difference from that maximum as a function of time. Doesn't that look like a wave? It's going up and down and up and down. Period's about 80 years. So so there are probably all kinds of modes in this system, right? So we know about the longitudinal mode, which is a Rossby mode. That's a weather system. The thing I'm not talking about, longitude. Love longitude. Thank God the sun's not flat, right? And then you've got the decadal mode, So the Rossby mode's period is about a year. The decadal mode's about 10 or 11 years. And then you maybe get into this sloshing, which is like a third order term, which would be about 88 years. Maybe you've also got something else sitting on top of that that's 400 years. I don't know how these things scale in harmonics, but you're looking at fourth order terms. This is probably the third one. But it looks a wee bit ratty in the sunspot number. But when you compare it to the geomagnetic indices are pristine. Look at that thing at the bottom. So I've flipped color table on you now. So this is comparing the sunspot record to the geomagnetic indices. Same thing. Right, so you see that beauty? It looks like a sine wave. So, and then of course for context, I've always got to put the Hill cycle on top of it because that's the monster lurking at the bottom of the ocean, right? Getting to the end, I ran through that a lot faster than I thought. Is anyone in the path of totality? Well, this is what the sun.
I plan to be.
This is what the sun's going to look like. Good luck. You don't have to go see it now. Sorry, I'm kidding. This is a website that some of our colleagues are putting out, which is doing kind of real time. As updates to the magnetic field are included, it does a real forecast of what the eclipse is going to look like, and you can even go in and look at your location. It's pretty cool. It's very cool, and they've been slowly improving their skill over the last few eclipses. So if you get the chance, scan the QR code and go and mess around with that if you're interested. And at that, I think I'm done. Hopefully that was interesting and not just bogged down on updates of where cycle 25 happens to be. We're back at cycle 4. Not satisfied with 25. I'll go back to 4.
It keeps getting more and more exciting every time you give one of these presentations. And looks like we're going to be in for some more ham radio stuff coming on in 25 and maybe into early 26.
Yeah, I think you're going to have hopefully have a nice duration in the declining phase, Paul. The one element I didn't get into, here's the inference test. So I was spend a lot of my time talking about, big El Niños and stuff in the late 1700s. What the hell happened to cycle 24? Do any of you remember what happened in 2003? Yes, Peter?
Well, you mentioned you wanted to go to the Admiralty. I might point out that you might want to check out the records of the Erebus and the Terror.
Yeah. I've got those.
You've got those? Yeah, because those were specifically looking at making magnetic measurements as they traveled from Britain to Antarctica, and also when the 2 ships went north into the Arctic.
The good old Franklin experiment.
Yes, it was Franklin's last expedition.
Yeah.
It was also Ross's first expedition to the Antarctic.
Yeah, it didn't end very well for many of them. So,
well, the Antarctic stuff was okay. It was the northern one.
Yeah, no, it's the Arctic one that didn't do so great.
Yeah, they all died on the northern one.
Yeah, may have eaten each other. So,
2003. It was the end of mid-October. I was driving back from North Bay, which is Northern Ontario, in a convertible, and looking up at purple aurora at 44 degrees north. Is that the event?
Yeah, well, we had aurora over the Flatirons here in Boulder.
Yeah.
That's the Halloween storms.
The Halloween storm. Right? That was phenomenal.
Yeah, I was on console. I was working at NASA Goddard at that time, and I was on console for the spacecraft, and the sun just started barfing fire at us, right? They were like, what do we do? What do we do? Right? So safing all the instruments and all kinds of stuff. Unsure. That's when it saturates the X-ray detector, you're in trouble.
It was for those of us in Canada and saw it, it was, I don't think I've ever seen anything since.
So the hypothesis there is that, of course, that those storms slowed down cycle 23. It's the same way as the big ones slowed down the granddaddy back there, right? Maybe not to the same degree, but it was enough to disturb what came next. Right? So just wait. It'll take us 10 years to get this paper published.
So are we going to get a big El Nino in this cycle? Is that what you're?
I think we're headed for a La Nina this year.
A Nino, yeah.
You're gonna ruin my skiing again.
La Nina, the weather's going to be effed up.
There was a fairly significant, I think it was a coronal mass ejection, in the last week that traveled from the sun much faster than usual.
Sunday.
Yeah.
Any explanation about why it was going so fast?
28 hours it took.
It was like going much more than 50% faster than usual.
It was clocked at 1,700 kilometers a second leaving the sun. And then when we measured it at 1 AU, it was going at 800 kilometers a second. So there's all kind of hypotheses out there about how that happens. The interesting thing is that none of our models take the solar wind into consideration, really. Right? So they're purely ballistic models. They're not the forecast models are not as advanced as the research models. Let's put it that way.
Okay.
And so they don't have the feedbacks that the kind of full complexity sun has. So, I think if you fold in some of that complexity, you could get there. But the problem is that there's not much understanding, Peter, of how the solar wind works.
Mm-hmm.
Right? It's you always hear me talking about the light side and the dark side of activity. The light side gets all the attention and nobody gives a shit about the dark side. Except weird people like me, because I'm a spectroscopist by training.
Mm-hmm.
And, I always make a joke with the kids. Some kids get it. But, I always say that if you looked at the sun through Doppler glasses, all you would see is the coronal holes. Right? Whereas if you looked at the sun through your retina, all you see is the sunspots, right? In the active regions. If you've got your UV goggles on. So, and I said, we just think about how that energy works, right? We know that the energy reservoir is exactly the same. The only thing that changes is the magnetic field above it.
Magnetic fields, yeah.
And so think about a huge active region, especially one as complex as the one that erupted on Sunday, whatever day that was.
Mm-hmm.
It was an existing active region that had been around for 2 or 3 rotations, and something emerged right in the middle of it that was almost rotated 90 degrees to it. And so when we say that, if you can actually look on our Twitter feeds, we spotted that this thing is popped up in the middle. I was like, watch, if things follow the way they normally follow, there's going to be a kerplunk pretty soon, right? And there was, and both of those regions went off at pretty much the same time. So, flight of fantasy, you open up. So, you've got a closed magnetic field. You generate plasma that's 5 or 10 or 20 megakelvin hot, and then you blow the top off of it. Right? What that energy reservoir doesn't switch off for the 24 hours that the thing's open, right? So what happens to all that energy?
Mm-hmm.
It's radiating out behind that storm, right? So the big question would be, does it actually help propel it? All right, is it a source of momentum for the CME? Because the CME is like a big magnetic bubble, or like a hot air balloon.
Yeah.
But if you're it's like back to Newton's laws, right? If you're providing an unbalanced force, the thing's going to just keep going. So anyway, until someone builds my full disk Doppler imager that I've been trying to build myself for 15 years, that's one of the things I hope to prove. Right? We've just built a Doppler imager. Does about 7 different wavelengths down in the guts, in the gook of the atmosphere. And so when these big things go off, we should get a definite Doppler signal. And so the question is, can we actually start to feed that into some of the forecast models to see if we can get them closer to what we actually see.
Beyond the
And then it's-
10.7 centimeter, is there any other radio record?
that goes back to 47.
Well, no, just it even goes back 20, 30 years, or like satellite type. Is there any radio type?
From Mauna Loa, we have
Data
stuff
sets.
going back to the late 60s. Chronal measurements. The routine chronal measurements started kind of in the Skylab era.
Yeah.
Right, we've got some going back, but they're not, and there's some from all over the place, but they're not routine. They're research.
Yeah.
Right, the photosphere was easy.
Experiments. Yeah.
You know, as you go up the atmosphere, then you have to get into orbit to see it because it's faint, right? And you've got to build chronographs, and chronographs are really finicky instruments. So, I mean, my hat off to these guys, Bernard Leo and these guys that invented the chronograph. It's absolutely, if you've ever seen an early chronograph, they are truly outstanding pieces of engineering.
Mm-hmm.
Massively underrated. So, of course, because this thing baffles out, just like the moon does on April 8th, it baffles out the light from something that's 1,000,000 times brighter.
Yes.
Right? So, anyway.
By any
Sorry, Paul.
chance, I don't mean to dominate here, but by any chance, do you happen to have an explanation for the shadow bands during the total eclipse?
Oh, no. Nope.
Do we know?
Oh, I'm sure someone does.
I've never found an explanation. Anybody on the line here know anything about the shadow bands during a total eclipse? If you don't know about them, and if you're going to be in the total zone of totality, just before the diamond ring, both the one that is the beginning and the one at the end of the totality, if you look on the ground, you will see bands of shadow, light and dark, very, very, not very dark, racing across the ground, all in parallel with each other. But then at the next diamond ring, when you look on the ground, they'll be racing across the ground in a different direction. Not the same one that you saw when it first starts. Completely different direction, not opposite. It's a completely different direction.
So what you're telling me,
Oh,
Peter,
there's
is
a shadow band.
I need to fly my drone up about 100 meters, taking a shot of the ground so we can see them.
I was
Yeah.
thinking of doing that actually.
Yeah, you probably wouldn't even need to be 100 meters,
Well, you need to have a high enough frame rate.
but that's a good idea.
If you can do difference imaging too, you should see them dead easy. But yeah, no, the eclipses are always fun.
Mm-hmm.
Just remember to take your glasses off.
Yeah. Thank you very much for everything you've done tonight, Scott. Appreciate your time, and you illuminated our minds again. And we hope that we will be able to see this continue on as we go through the rest of the cycle and into the next cycle, 26.
Yeah, no, it'd be fun when we start to see 26. I have a funny feeling that you guys might be the first people to hear about it. So
I like that.
You know what's really funny is most of the people here, I don't know how many people here are actually HF operators versus VHF operators, because it's the HF operators that are really passionate about below 30 megahertz propagation.
Yep.
That's for sure. All right, well, I'm going to stop the recording, and if you guys want to stick around and chat some more, I'll leave the bridge up, and you guys can carry on.
Yeah, hopefully that wasn't too dull. So
no,
I thought I would spice it up with I was kind of hoping that Peter would be on so I could show him some of the ice core stuff. So